Let's have a look at problem 9.3 now. This is related to problem 9.2, so I recommend that you have a look at problem 9.2 before trying this one. So we are given two control architectures in figures 9.4 and 9.5, where if we draw the controller block, in both cases we have the disturbance D once entering inside the control block and once entering outside, and we're supposed to calculate the transfer functions from D to Y. Let's assume W and V are identically 0 at all times. So now we can write down the plant dynamics as Ax plus Pup. Let Up be the input to the plant, and Y is then Cx. The estimator dynamics are then basically first just the copy but with now the UE, with UE being the input seen by the estimator, and the estimator gain multiplying the output errors, which then gives us the estimator dynamics as shown here. Now the plant dynamics are excited always in both cases by UP, which is given by F times the estimated X, which is X hat, plus a disturbance D, whereas the estimator sees UE as either the true, so either AF X hat or Fx hat plus T. So this is from figure 9.5, and this is for figure 9.4. So you can see that in 9.4 the estimator sees, so let me draw, so this is UE, and this one is UP. So note that in both cases the input to the plant is F times X hat plus D, so F times X hat plus D, whereas the estimator sees two different inputs in these two different figures, and this is what we have to investigate now. So now let's write down the closed loop dynamics for these two cases below. So let's first do it for figure 9.4, which is this one. So if we combine now the plant and the estimator dynamics, we get x dot is ax plus bup, and up is f x hat plus t. So we get ax plus b f x hat plus b t, and x hat dot is now a plus fec plus b f x hat plus bd minus fecx. We can write this in matrix form now as a pf minus fec and a plus fec plus pf times x and x hat plus p times t. Now for figure 9.5, we have the same plant dynamics, but the estimator dynamics are now using this input seen by the estimator. We have a plus pf plus fec x hat minus fecx. So that now in the matrix form looks like so the first matrix remains the same, but now we have a 0 here to x cap. Now note that we have x and x hat as the state variables now. Now if I pre-multiply both sides by identity blocks, or identity minus identity blocks, I will get the error dynamics and so if we do that, we get E dot as A plus FEC times minus A plus FEC x hat plus 0 times t, which is A plus FEC times E plus 0 times t, and this is because we have PB repeated here and we have I minus I PB is 0. Note that In the other case, we don't have this, and we will get A plus FE C times E plus B D. And because of this, we see that the error dynamics are uncontrollable from D in the case of figure 9.4, whereas they are controllable from D in the case of figure 9.5. So in the case of figure 9.4, we will get the transfer function from D to Y the same as if in the case of state feedback. So now in order to compute transfer functions, we can simply add the output equation to both these dynamics, which is nothing but C0 x hat, and the same here. So now we have the state space models for both control architectures, and we can compute the transfer functions for both cases as simply C times Si minus A inverse B. And this I now leave it to you, because we have all these matrices C, A and B. Yeah, and that's it for this problem. Thanks a lot.